All right, today's lesson is 5.2, circumcenter, incenter, and centroid. Go ahead and take care of your notebook and get your objective down in your notes. All right, before we begin, we have some new vocabulary. We're going to talk about the word concurrent. Last year in algebra, we talked about intersecting lines, but that was only with two lines. In geometry, because we're working with triangles, we're going to be working with lines that, generate from the vertices, and triangle has three vertices, so we're actually going to have three intersecting lines, and sometimes more as we get further into geometry. So when we have three or more lines that intersect at a single point, we're going to call that concurrent lines, and the intersection point where they all meet is called the point of concurrency. All right, every triangle has four interesting points of concurrency. So, in each one is represented by a different feature of the triangle. So, for example, the circumcenter is the first center of the triangle we're going to look at, and it is created by the perpendicular bisectors of the triangle. So, if you look closely at this diagram, you can see that I'm going to look at this line segment right here. I've got a perpendicular line, and then I've got congruent segments here, which means that is the perpendicular bisector. And I could do the same thing for each of the other lines. Let me get some different colors up here so we can see what's happening. So this guy right here is bisecting this segment, perpendicular bisector. And then let's pick red. So I've got this guy right here, perpendicular bisector. Okay, so the place where the perpendicular bisectors meet is that spot right there, and that is called the circumcenter. All right, interesting thing about the circumcenter is it also happens to be, and I don't know how this happens, it's like a geometry miracle, that it also happens to be the center of the circle that is circumscribed around the triangle. So this point right here is where the perpendicular bisectors meet, but it is also the center of that circumscribed circle. All right, the next one we're going to talk about is the incenter. And the incenter is created by the angle bisectors. So if I look at this line right here, I could say that angle 1 and angle 2 are congruent. And then this guy here is bisecting this angle right here, so these would be congruent, 3 and 4. And then I would also have this guy, oops, got a little off track there, bisecting that angle, so angle 5 and angle 6 would be congruent. So they also meet at their own special point, and that is called the incenter. So they are created by the angle bisectors, as opposed to the perpendicular bisectors of the circumcenter. Okay, the third center we want to talk about is called the centroid, and it is created by the medians of the triangle. So the median is the line drawn from the vertex of the angle to the midpoint of the opposite side. So I want to clarify the difference between the circumcenter, which is the image above here, where it was created by the perpendicular bisectors. Okay, so the perpendicular bisector would be this guy, going at a perpendicular angle and then bisecting the line segment. The difference between the circumcenter and the centroid is the circumcenter is created by the medians. So the median is the line drawn from the angle vertex down to the midpoint of the other side. You can see this is the midpoint because the markings are the same. So you can see all three of those medians are intersecting at the same point. Their point of concurrency is this point right here, and that is called the centroid. And the orthocenter is created by the altitudes. So the altitude we talked about earlier in the week is the perpendicular drop from an angle's vertex down to its opposite side. So I'm just going to drop a perpendicular straight down. That's the shortest distance. We also talked about that, and create a perpendicular line. So I could do that with each of these. Shortest distance is the perpendicular line, and where all the altitudes meet, that is called the orthocenter. Okay, so today we're going to focus on a few of these, so make sure you get your notes ready. All right, circumcenter. In your notes, the point of concurrency of a triangle's three perpendicular bisectors. So go ahead and pause and get the information and the image in your notes. The circumcenter can be on the inside of the triangle, on the triangle, or outside of the triangle. So depending what kind of triangle you're dealing with, it's going to determine where the circumcenter lies. So if I have an acute triangle, the circumcenter is going to be inside the triangle. So an acute triangle, the circumcenter is inside. If I have a right triangle, where this would be my right angle, the circumcenter is actually on the hypotenuse of the right triangle. So it's on the triangle itself. And then if I have an obtuse triangle, say this angle is, I don't know, let's say it's 105 degrees, an obtuse angle, the circumcenter actually ends up being on the outside of the triangle. Circumcenter properties. The distance from the circumcenter to each of the vertices of any triangle are congruent. So here's my perpendicular bisectors. That means that's congruent. Here's my second one. That means those are congruent. And here's my third one. That means these are congruent because the circumcenter is created by the perpendicular bisectors. This is the circumcenter. So the interesting property about circumcenter is that the distance from the circumcenter to each of the angle vertices has to be congruent. So let's say if this is 3, then this has to be 3, and this also has to be 3. They have to be the same distance. Okay, and then we also already talked about the circumcenter being the center of the circle circumscribed around the triangle. All right, first example, DG, EG, and FG are the perpendicular bisectors of triangle ABC. So perpendicular bisector means that's congruent. Those are congruent. And finally, these other two sides are congruent. This is the circumcenter. So it says find the distance of GC. So I'm trying to find GC. All right, well, I know that GC and GB have to be congruent to each other because they are the distances from the circumcenter to the angle vertices. So since BC is 13.4, GC also has to be 13.4. All right, and there is your reasoning if you would like to put that in your notes. All right, use the diagram to find GM. All right, let's go over here and find where GM is. That's this guy right here. Okay, given MZ is a perpendicular bisector. So MZ is this guy right here, perpendicular bisector. Okay, so it looks like MJ is 14.5. This distance right here is 14.5, which means MG or GM also has to be 14.5. A lot of these you're going to be able to figure out just by using your common sense. Use the diagram to find GK. All right, GK would be this line segment right here. And you will notice that GK, because if this is a perpendicular bisector, that this segment has to be congruent to this. And they've actually given me a measure for the second half of this segment, which is 18.6. So this is also 18.6. Now, if you were thinking it was 19.9, you didn't look closely enough because the 19.9 is actually talking about this other segment here. So make sure that you're reading your drawings correctly. Use the diagram to find JZ. All right, JZ is here, which is the distance from the circumcenter to the angles vertices. So I think this is the one where I'm going to actually use the 19.9, because if this one is 19.9, then JZ also has to be, oops, not 19.2, 19.9. All right, given isosceles triangle ABC with AB is congruent to AC. So let's start out with our proof, with our statement and our reason. And let's see, CD perpendicular bisector of AB. That's given. All right, what is that going to do for me? CD is a perpendicular bisector. I'm sorry, that's GD. I read that wrong. GD is a perpendicular bisector of, let me make this more clear. GD is a perpendicular bisector of AB. So GD, perpendicular bisector. Okay, so right away I know that AD and BD are congruent. AD congruent to BD. Definition of perpendicular bisector. All right, given GE is a perpendicular bisector of AC. All right, let's use a different color. GE, perpendicular bisector of AC. I'm going to shorten this up for sake of time. So this is going to go down here, and that's going to be given. From that, I can say that AE is congruent to EC by definition of perpendicular bisector. All right, so let's see what I've got going on right now. All right, if I have two perpendicular bisectors intersecting, I really don't even need that third one. So I'm going to say that this is the circumcenter. So point G is the circumcenter of that triangle. So I'm going to I'm going to erase this stuff here so I can have some little more room without scrolling down and losing my image. So point G is the circumcenter. Okay, and that's definition of circumcenter. Where the perpendicular bisectors meet. Okay, since G is the circumcenter, GB and GC are congruent. And I'm going to say that's properties of circumcenter. The property of a circumcenter is that the distance from the circumcenter to the angle vertice is congruent. All right, which means this is congruent to this, and it looks like now I have two congruent triangles by hypotenuse leg. So the triangles are congruent. These triangles are congruent by hypotenuse leg. All right. Incenter. The point of concurrency of a triangle's three angle bisectors. So if you look closely at the picture, each angle is being bisected. I can see by the markings. That one's got one marking, this one's got two, and the other one's got three. So the point of concurrency is called the incenter. Properties of incenter: the altitudes from the circumcenter to each of the sides of any triangle are congruent. So I know this drawing's a little confusing. So let's draw our own incenter. All right, I'll walk you through it. So first I need a triangle. Let me get a triangle like this. Let me get that other one completely out of the way. All right, so I'm going to draw my incenter. Okay, these are approximations. I'm just going to try and hit it on the nose and see what happens. So I need three angle bisectors. So I'm going to, let me get a different color here so we can see what's going on. All right, so I need an angle bisector. So that looks like maybe it's cutting that angle about in half. And then I would need one for this guy. That one's going to be the harder one to see. These smaller ones are easier to determine. Okay, so I've got 3 angled bisectors there. All right, so that means that these 2 angles are congruent, these 2 are congruent, and then my last 2 are also congruent. 3 angled bisectors, where they meet, that's going to be my incenter. All right, the property says if I drop an altitude from the incenter to each of the sides of the triangle, those will be congruent. So an altitude is the vertical drop, the shortest distance from a point to a line. All right, so the vertical drop on this guy is going to be from here to here. That's the altitude of that guy. And these are just approximations again. I'm just trying to make it look like it's 90 degrees. Okay, and that's my vertical drop from that guy. And this guy almost looks like it might be 90 degrees already, so I'm just going to go ahead and go with that. Okay, the property of the incenter says that the 3 altitudes that are dropped from the incenter are congruent. So for example, if this is 2, then this other guy has to be 2, and this other red guy has to also be 2. Unlike the circumcenter, the incenter is always inside the triangle. So it's not going to go outside or on the triangle at all. It's always going to be completely enclosed by the triangle. Doesn't matter if it's acute, obtuse, or right triangle. All right, so I've got 3 perpendicular drops, it looks like there. And I'm trying to find, it should say these angles are congruent, okay? That should have been given in the problem, that these are angle bisectors, which makes this is the incenter. So the perpendicular drops are all going to be congruent. So this has to be congruent to that and that and that. All right, if PT, which is this guy right here, if that guy is 3, it says find PU, that's this guy. Well, they have to be congruent because they are the altitudes from the incenter. So they are both going to be 3. All right, find PV, same situation, if PW is 7. So if PW is 7, then PV, which is here, also has to be 7 if those are points from the incenter, or lines from the incenter drawn to the sides of the triangle. All right, MP and LP are angle bisectors of triangle LMN. Find the distance from P to MN. All right, so the distance from P to M, the shortest distance, that should say shortest distance up there from P to MN, would be the perpendicular drop. That's the shortest distance. All right, it says I'm given that MP and this guy, MP and LP, are angle bisectors, which means they're meeting at the incenter. And I'm seeing that this perpendicular drop has a measure of 5, which means LP, the one I'm sorry, P to the distance, a distance of P to MN. So this distance would also have to be 5. If this is 5, that's also got to be 5. QX and RX are angle bisectors of triangle PQR. QX and RX. Okay, so here's QX is the angle bisector. That means this and this are congruent. Those 2 angles are congruent. And RX is also an angle bisector. Let's pick a different color. RX is an angle bisector. That means this angle is congruent to this angle. Angle by definition of angle bisector, find the distance from X to PQ. All right, here's PQ. I need to find the distance from X, which is my incenter. I'm sorry, it's the incenter where the angle bisectors meet. I need to find that perpendicular drop, which is going to look something like that. All right, I can see that one of the other perpendicular drops has a measure of 19.2, so that means that this one would also have to be 19.2. If that's 19.2, they are both 19.2. All right, a little bit of a summary. Circumcenter where the perpendicular bisectors meet, and the distances from the circumcenter to each of the three vertices are congruent. The incenter is where the angle bisectors meet, and the altitudes from the incenter to each of the three sides of the triangle are congruent. So if these are the angle bisectors, this is what we just did. This is the incenter. The perpendicular drop from the incenter are all congruent. All right, one more thing we're going to cover, medians of a triangle. The segments extending from the vertices of a triangle to the midpoint of each side. So while it looks like they're angle bisectors here, not necessarily so, but all I know for sure that it is going to the definite midpoint of the other side. So each angle, a line drawn from each angle to the midpoint of the opposite side is going to give me something called the centroid. So where these three lines are concurrent, their point of concurrency is called the centroid. So let's see what the bottom part says. The longer piece of a median of a triangle extending from the centroid is 2/3 the length of the entire median. All right, example, if FO is 9, if FO is 9, the whole distance is 9. Okay, that means that FI equals 2/3 of 9, and IO has to be the remaining 1/3 of 9. All right, so if you do your math, 2 times 9 is 18 divided by 3, which is 6. And 1/3 of 9, 9 times 1 is 9, divided by 3 is 3. Okay, and they do add up to be 9. If IS is 2, find IM, bottom part. If IS is 2, this is 2. Find IM and MS. All right, well, if IS is 2, I know that is 1/3 of my total distance. Okay, so 1/3 of some number is equal to 2. All right, that's going to give me my whole distance. So if I multiply both sides by 3, that's going to cancel this out, and I'm going to end up with x is equal to 6. So the whole distance, MS, is equal to 6, and IM has to be 2/3 of that. All right, so IM equals 2/3 of 6, which is going to give me 12/3, which is 4. And that actually makes sense. Like if I have a line segment that's divided into 3 equal pieces, okay, the first one's going to be 2. The last one has to be doubled up of 2. So the last one is going to be 4. All right. The altitudes of a triangle, segments that extend from the vertices of the triangle to the side of the triangle, are perpendicular to the sides. So, all right, we kind of talked about that the other day. The altitude is a line that's drawn from the triangle vertice. It's a perpendicular drop drawn. It doesn't necessarily bisect it. It just is a perpendicular line. Okay, so clearly in that picture, these two line segments they're not congruent. So you can't say that it bisects anything. All right, it's simply the perpendicular drop. All right, that's it for today's lesson, and have a great day.